Good morning. We begin lecture 28. Today we will conclude our discussion on the two-channel filter bank and begin a new section on OFDM. So there were a few questions after the lecture yesterday, so I thought I would just clarify. We are looking at a two-channel maximally decimated filter bank. The first question is, why maximally decimated? Maximally decimated basically means that whatever is your input sample rate, number of samples per second, will be the net sample rate across these different subchannels. If you did not do the downsampling by a factor of 2, you can find that if you split it into two channels, the number of samples per second will go. So maximally decimated, one of the key reasons is because we want the sample rate to be the same, want the number of samples per second to be constant or be the same, right? Otherwise we would end up having to store more information. So this is one of the key reasons why we have maximally decimated. The second element is, what is typically the processing that will happen with these subchannels. The processing that happens with the subchannels invariably is in the form of compression. At this point it is usually compression for storage, compression for transmission. Then why do we need the reconstruction? At the other end you would have to recover the original signal. So typically these signals which have been compressed have to be uncompressed and then recombined to form the original signal. So how do you test whether your recombining section is working properly? The way you do that is, assume that there is no compression. Can you recover the original signal? Exactly. If you can, then your reconstruction part is working fine. You kind of have to test it under the case of no compression. But if you are not going to do any compression, then there is really no, why do you split it and then recombine it? But the whole reason is you are splitting for a very specific purpose like compression or storage, and then at some point you will want to recover and retrieve the signals. So the input output relationship, we will not revisit it, basically can be written in terms of the input signal and the alias signal. The constraints that we have used in the past, this is for alias cancellation. This always guarantees that aliasing is cancelled. We also wanted to force a relationship between H1 and H0, and one of the ways in which we said was this was option 1. And this brought us to a point where we could make some trade-offs between phase and magnitude errors, but we could not eliminate both of those. So the QMF condition basically says that if you go with this QMF condition, let me just write it down here. With the QMF condition, what you will get is T of Z is equal to 1/2 of H0 squared of Z minus H1 squared of Z. Okay. And we from this point on, we looked at 3 variations. Let me just quickly remind you, this is more of an overview. So the first solution 1, where we have implemented the aliasing cancellation and the QMF condition, you have got T of Z of this form. The first solution was, let us design H0 of Z as an FIR type 2 linear phase, filter. Okay. Then what we get is the transfer function T e of j omega is equal to e power minus j omega n divided by 2 mod H0 e of j omega magnitude squared plus magnitude H0 e of j omega minus pi whole squared. Okay. Now how did we design H0? H0 we said would be design H0 via optimization, and it will have 2 parts that you will try to optimize. The first one is stop band attenuation, because all filters, if you want to have a good, and typically you would have to have a passband criterion as also, but in this case we said the passband criterion need not be optimized separately, we will impose a flatness constraint on T e of j omega, The flatness constraint is what is given here, and once you ensure that you have good stop band, automatically the other filter will have a good pass band. So again, this was a case where we could cancel aliasing, no phase distortion achieved, no phase distortion we were able to get, no magnitude distortion via optimization. So this is I can't put a tick, I can't put an X, I kind of put a tick and an X. Okay, so basically yes, I have done it via optimization, but it is not fully eliminated. Okay, so I cannot say no magnitude distortion, some residual may be present. Then comes solution 2. Solution 2, we said we will split H naught of Z into its polyphase components, E naught squared plus Z inverse E1 squared. We also showed that this, if you carry it through, will give you T of Z to be equal to Z inverse E naught of Z squared E1 of Z squared. We said now can you find filters where you can have E naught and E1 as delays, not good filters, but if you can choose them to be all pass functions. So we did manage to get demonstrate that you can do H naught of Z to be equal to 1/2 of A naught of Z squared plus Z inverse A1 of Z squared. Basically the polyphase components are all pass, which gives us T of Z to be equal to Z inverse by 2 A naught of Z squared A1 of Z squared. Okay, no, in this case there would be aliasing cancellation, magnitude distortion, I am just going to write as magnitude, and the phase distortion no. No, phase distortion has not been satisfied. We also saw a solution 3 which was of the same genre, where we said that we will enforce the constraint H naught of Z, H1 of Z to be power complementary, and we also said that these filters are IIR filters with certain specific properties. P naught of Z by D of Z, H1 of Z is P1 of Z divided by D of Z. This P naught is symmetric, P1 antisymmetric. We finally showed that T of Z comes out to be 1/2 of A naught of Z, A1 of Z. Okay, again it is the same category as before. So whatever we saw here is applicable here as well. No aliasing, magnitude distortion is removed, but phase distortion is still present. Okay, so the same criteria or conditions or observations apply here as well. And so the final step that we took yesterday was the 2-channel case, where we said we will do aliasing cancellation in this manner, and instead of choosing the QMF constraint where H1 of Z is equal to H naught of minus Z, we said we will take its paraconjugate with the delay so that it becomes causal. So it is alternate to the QMF, right? It is a QMF alternate. It is basically saying the same thing. The magnitude response is the same as H naught of minus Z, but you have taken it in the form of its paraconjugate. Given this choice, go back and substitute and verify that the transfer function comes out to be T of Z, where T of Z is Z power minus n. I believe yesterday when I wrote in the class, I wrote it as 1/2 of Z power minus n. Please do make a correction, it is Z power minus n. Okay, so this is the one that actually gives us the perfect reconstruction, and therefore the exactly what we are looking for. Okay, so this is solution 4 or more importantly the one that gives us perfect reconstruction, probably the most important of the 4 options. It did take us a while to actually develop the perfect reconstruction solution. On the way we had to actually bring in the paraconjugation, because without the notion of paraconjugates this would not have been justified. Just out of the blue you pull something out, but the fact that we started to think about paraconjugate in the context of all pass functions and then eventually applied it in the context of the 2 channel case hopefully gives you a complete picture. Now just a comment about the design and I think we will then wrap it up with that. I want to design a half band filter. Why half band filter? Because half band filter has got the property that when you shift and add, it will add up to a constant. Now if I factorize the half band filter, then I will get a power complementary set. So that is where we are going towards, because if you remember we are interested in power complementary property, we also are interested in the half band property. So we initially say that I want to design a linear phase. We are going to have to specify the order as even but not multiple of 4, okay. That means it would be of the form 4j plus 2, and the reason is, one, when you spectral factorize it, it will come out to be an odd order filter which is exactly what we need to get perfect reconstruction. And and anyway, if you want to do a half band filter, you would have to specify it to be even but not multiple of 4. That is the only way you can satisfy that condition. So if I have designed my filter to have a ripple of delta in the pass band and a ripple of delta in the stop band, and I am showing it as equiripple because these linear phase filters have got a program called the Parkes-McClellan program, which gives you the Parkes-McClellan which give you equiripple filters, and equiripple filters are optimal in terms of order. So why not treat it as equiripple? So again half band, but now what else do I have to do to the half band? In this form it is not factorizable, because notice that the amplitude response has got both positive and negative. I would have to lift the magnitude response by delta. So I take the 0 phase response and then lift it by a term delta, that gives me G naught E of j omega. So basically the whole thing has moved up. The peak limit is 1 over 1 plus 2 delta, the lower limit is 0, the stop band ripple is 2 delta. Okay. At this point we can make the following statement, that G E of j omega is strictly greater than or equal to 0. So therefore I can write it as something magnitude squared, and that is where we get the statement that G0 of z now can be factorized as H0 of z tilde times H0 of z. Spectral factorization requires you to have that, because when you look at it on the unit circle, the right hand side will be something magnitude squared. So you cannot get something which has got negative valued functions on negative values on the left hand side. Okay. Once you have done that, you can verify that you have a filter whose order is 1/2 of the original half band filter. So this filter has got order is 2j plus 1, order 2j plus 1. Okay. And of course when you look at the zeros of G naught of z, you can argue that basically they will occur as quads, and all of that we can go through. The zeros on the unit circle will be double zeros, so therefore you can factorize one of them to H naught, the other one to H naught tilde. One last point about the design process. So this is the design continued, more of a closing comment. Now what is your upper limit? What is the peak value that you are seeing here? That is 1 plus 2 delta, okay, and the stop band is also 2 delta. Those are the two values, okay. But now if I want to treat this as something magnitude squared, so if I want to visualize this as H naught E of j omega magnitude squared, okay, then the first thing that I want to do, I want to look at is the maximum value of H naught that I will get for H naught E of j omega magnitude. The maximum value will be square root of 1 plus 2 delta. Okay. So, if I want H naught to have a maximum magnitude of 1, then what I would do is take H naught of n and then scale it by 1 over 1 plus 2 delta. It is straightforward to get the scaling, and therefore, so this will be a normalized value of the filter. Okay. Now, I just want to look at what is the stop band attenuation that we will achieve for the H naught. Okay. So, if you think of this as the stop band of H naught magnitude squared, then I would have to call this as delta 2 squared. Okay. So, delta 2 squared delta 2 squared is equal to 2 times delta, right. So, 2 delta is delta 2 squared. Now, if I want to write it in terms of the wait a minute, did I get that correct? Yes. So, so if I want to, or this is in other words, delta is equal to where delta is the ripple of the half band filter. So, this would be delta 2 squared divided by 2. Now, if I wanted to write this in dB, just so that we complete the discussion, conversion to dB or attenuation will be minus 20 log base 10 of the stop band ripple. That will be the attenuation for the half band filter. That is related to the stop band ripple of the filter H naught in the following relationship: minus 20 logarithm base 2 of logarithm base 10 log base 10 of delta squared minus 20 log base 10 of 2. Okay, I am sorry, delta 2 squared, correct, delta 2 squared. Okay. So, if I were to write it in terms of the attenuations, this would be AS prime, that is the half band filter is equal to 2 times the attenuation of the filter H naught, because it is delta 2 squared. What I should have taken is delta 2, but when I take it, it will be twice that, plus 6. Okay. Now, why is this even important for us? Because if you want to specify a certain attenuation for your H naught, right, if you want to specify a certain H naught of Z must have attenuation of, let us say you want to have attenuation of 40 dB, stop band attenuation of 40 dB. How will you achieve it? You have to go back and tell the specification for the half band filter. What will you specify the attenuation of the half band filter as? 86 dB. Only then, after you go through the lifting and the factorization, you will get the correct value. Now, if you are going to normalize by 1 over square root of 2 delta to get the maximum magnitude to be equal to 1, then what will be the magnitude of the stop band ripple? Instead of delta 2 will be, if you did not normalize, if you normalize, it will become delta 2 divided by 1 plus 2 delta. Okay. So, you may want to assume that you are normalizing everything and then rewrite the equation for the attenuation, but keep in mind that we now have to design a half band filter which is much more stringent than the actual filter we are trying to design. That is always the case when we have to do spectral factorization, because the parent filter must have better attenuation. When you then factorize it into two parts which are paraconjugates of each other, each of them will have poorer performance than the parent filter, because it comes with a magnitude squared relationship. Okay. That completes the discussion on two channel. So, basically to go back and say that we now have a way of designing the analysis filters and the synthesis filters from one single filter. Which one is it? It will be a half band filter, which you will design with the appropriate attenuation and scaling, then take its spectral factorization, that will become H naught, and then the mirror image filter, not exactly the QMF version, but you will want to make it the paraconjugate, becomes H1. Then correspondingly F naught and F1 are chosen to cancel aliasing, then you are guaranteed that the input output is in the form of a delay LTI system, which gives you perfect reconstruction.